Now let's calculate the capacitor CO2. CO2 equal to, but before that you need to calculate the size. So how will you find the size? So we need to find the size of M3. How will you find the size? So first you need to see what current you are designing for. Okay, so assume max load current equal to, let us say 10 milliamp, and M3 has to be in saturation. Let us say your VDD is 1.8 volt plus minus 0.1, which means VDD mean is 1 point or plus minus, not, let us make it 2, because usually we consider 10%. So VDD mean is 1.6 volt and V out max equal to 1.5 volt, let us say. So we have to size for the minimum VDS. So the condition for saturation is your VGS minus VTH should be less than VDS. Okay, and in order to reduce VGS minus VTH, we have to increase the size. So which means you have to sizes for a minimum VDS required. So that's why I am considering the minimum VDD and maximum V out, that will give you the minimum VDS or minimum dropout voltage. Okay. So your V drop out equal to your VDS min equal to 100 millivolt, correct? Which means W by L should be determined for VGS minus VTH less than equal to 100 millivolt and ID equal to 10 milliamp. So you know mu Cox already, ID is known, W by L can be calculated from there. So do the calculation again using this equation, ID equal to mu Cox W by L VGS minus VTH whole square, 10 milliamp half, I will put it 50 micro W by L, and this is 100 millivolt per square. So what is W by L? (20 milli over 50 micro into 10 to the power 4 into 10 power minus 6. Okay. So this will be your how much? So 12 minus 4, 8. So 20 into 10 power minus 3 over 50 into 10 power minus 8. Correct? So 20 over 50, 10 power minus 5, which is how much? 40,000. Huh? No, for this we are not assuming 1 mile, because this device is very large. Huh? So for power FETs you usually keep minimum channel length, otherwise your area will be bloated. Huh? Your chip size will be very huge. So for power FETs we usually consider minimum channel length. For those smaller devices you use is a larger channel length, but for power FET you don't, because this is a driver which is basically driving very high current. So this is your W by L ratio. So what is W? W is 40,000 multiplied by 0.18 micrometer, which is how much? 7,200. Now W by L is how much? W into L basically.
1296
Pico? What is pico here?
because
I am asking for area. 70.
pico meters, because into 10 power minus 12 will come final.
Just tell me the number, don't tell me the unit. 7,200 multiplied by 0.18. How much is that?
129.
Okay. Micrometer square. Correct. And we know that what is the cap? C 5 femtofarad. So what is the capacitor at this node? What we call it? CO2. Okay. CO2 equal to 1296 multiplied by 5. 6.48 picofarad. Okay. Now compare the previous cap we calculated at CO1. That was 50 femtofarad. Now we are getting 6.48 picofarad, and we know R out is also large here, 500K. So now calculate the pole. Omega P2 how much? 1 over 500K multiplied by what is the frequency? Can you do the calculation? So 1000 1 over 6.48.15 divide by 2 multiplied by
0.03
hmm?
3 into 10 power 5 radian. Approx.
3 into
3 into 10 power 5 radian per second.
wait 5 into 6.4 How much?
0.3 gigaradians per second.
So 300. 0.3 gigaradian.
Giga around
No, no.
3 million.
30 mega. Huh?
No, no. 0.3 mega.
0.3 mega. You guys are messed up. Okay, let's do calculation here. So this is 1 over 5 into 10 to the power 5 into 6.48 into 10 power minus 12. So how much is that? 10 power 7,
By you can approximate
5 into 6.48, which is roughly
0.03
0.03
into
10
10 power
power 7, which is 0.3 into 10 power.
6
So 3 into 10 power,
5
which is 300 kiloradian per second. Okay. Which is will quite likely fall within your UGB. Okay. So we cannot ignore this pole omega p2. Now third pole. Where is the third pole?
Third pole is the output of the pass.
Which is your, so C out. C out is a basically, it's not a fixed cap. I mean, this is external cap which you need to put at the output. Okay, it could be order of picofarad, microfarad, you never know. Okay, so we have to assume a value to start with. Okay, so let's assume C out equal to, so usually order of like tens of picofarad minimum you put, and maximum could be anything like even microfarad, you don't know. So C out assume C out equal to 10 picofarad, and what is R out? Because current is very high. Okay, so R out will be mostly determined by your load current 10 milli, and if your output is 1.5 volt, then what is the 1.5 divided by 10 milli will be your R out. So 1.5.
Practical is not neglected RDS.
No, at this high current, okay, this will be mostly determined by this. Okay, when you have a low current, then RDS will start coming into picture. Okay, so even if you calculate that way, I mean, you apply the same formula 1 over lambda ID. Okay, so it's a minimum channel length we are assuming. So lambda is approximately, if I consider 1. So what is your what is the transistor? M3. Huh? So RO3 is RO3 is equal to 1 over your current is 10 milli ID. So this is 100 ohm. Okay. Now in the load, if you consider as a resistive load, then you have to take it into parallel. If you don't consider the resistive load, then that will be very high. Let's say it's a current load. So in the current load, the resistance looking into the drain might be much higher, because you don't know what kind of current source it will be there. Okay, so there are two assumptions here you can consider as, but in both the cases your resistance will be much lower, like it cannot be even kilo ohm for 10 milliamp current. Okay, even if you let us say ignore this, 1.5 divided by 10 milli, it's 150 ohm. So you will always get order of ohms, not kilo ohms in at such a high current. So if you consider resistive load, then it will become 100 ohm parallel with 150 ohm. Okay, so let's say if you consider R load equal to 1.5 volt divided by 10 milli, which is 150 ohm, then your R out will become 100 parallel with 150. This will become 60 ohm. So 60 ohm and 10 picofarad, that's very high frequency. So your omega P3 equal to how much? 1.6, which is even higher than your first pole.